Swayam Prabha. Digital India. Educated India.
You get 4 pi. That's what this 4 pi is. So why I am saying this is because what is this, what is happening here? You are getting total curvature is 2 pi times chi. Okay. And this is the general theorem. If you take surface of genus G, okay, so how is this going to generalize? It's going to generalize like this. You take a surface of genus G like this, okay, which is basically a G torus, okay. Then its Euler characteristic is 2 minus 2G, okay. And if you calculate integral over the G torus of the curvature, Gaussian curvature function dA, which is the total curvature, okay. Mind you, integration is just summation, and this is since the point is varying on a surface, it's what is called a surface integral. So you are integrating on the surface of the G torus, and the function that is being integrated is the pointwise curvature, okay. So this integral will give you 2 pi chi. So it will be 2 pi into 2 minus 2g, so you will get 4 pi into 1 minus g. This is what you will get. This is the Gauss-Bonnet theorem, okay. Now, so I am saying that when g is 1, so what will happen is that, you see, if you put g is equal to 0, you get 4 pi, which is sphere case. You put g equal to 1, you get the torus. Torus total curvature is 0. Okay, that's an interesting thing, because what happens is that if you take the torus, okay, you vertically cut it by this central circle above and below, you will get an inner part which has negative curvature, and you will get an outer part which has positive curvature, and they will cancel out each other. So in the case of torus, what happens is that if you take one torus, okay, you will get chi is 0, and total curvature is also 0. And why is this true? This is because if you take this one torus, okay, this there is an inner portion which looks like this, okay, and then there is an outer portion which looks like this. This inner thing has got negative curvature, and this outer thing has got positive curvature, and you add both of them, you get 0. That's why it's 0. The total curvature is actually 0. Okay. Now the question is how. So I'm just trying to go back and forth. How did you get the formula for the? This is the Gauss-Bonnet theorem actually. So you can think that, see, what is the source of the Gauss-Bonnet theorem? At least for the sphere, for example, the source is actually this simple result, that the sum of the, if you take the excess of the sum of the interior angles over pi for a spherical triangle, that excess is actually the area of the spherical triangle. Okay. Now you can ask the following question. This is about looking at what is special in a spherical triangle. The edges are all geodesics. Okay, they are curves of shortest length. But what if you kind of take distorted curves which are not geodesics? That means the curves, they are not curves of shortest length. So you can ask that question in the plane itself. I'm going to come to another version of this. See, if you look at the plane version, you have this alpha, you have beta, you have gamma, then alpha plus beta plus gamma is equal to pi. You have this. Okay, but what is going to happen if I take a triangle like this? Okay, this is a curved triangle. It's what is called a curvilinear triangle on the plane. Okay, again here, mind you, I still have the angles alpha, beta, and gamma. I mean, whichever way you want to take it. And you know how to define these angles. The angles, you have to take tangents, okay? So you know the definition. So now the question is, how the way, if you, how are these alpha, how is alpha plus beta plus gamma related? Obviously, you're not going to, you should not expect to get pi. And why it's going to be distorted is because these are not straight lines, there's some curvature. So curvature is going to play a role. How exactly is the curvature playing a role? That is also a particular case of the Gauss-Bonnet theorem. So what happens is, what you do is that you take, see this curve, there are three curves. So I can call this curve as gamma 1, gamma 2, and let us say gamma 3 if you want. Okay, and I put what is, so the curves have to be given what is called orientation in such a way that the region you are considering is always to the left of the curve. So this is the orientation, so this is the region inside. Okay, so if you walk along the curve in that given orientation, the region that you are considering should be to your left. That is the correct orientation. Okay, now guess what is going to happen. What is going to happen? See, if you take each of these curves, on each of these curves, there is a curvature function. If you give me a point on this curve, there is a k of p, there is a curvature function, and here it is called, what is called as sine curvature. Okay, the sine curvature is supposed to keep track of whether the sign is given to keep track of whether the curve is going concave in one direction or convex in one direction. Mind you, how this comes is when you take a curve, what is curvature? You take a curve, then at a given point you have a best fitting circle, that's called the circle of curvature. Its center is called the center of curvature, and this radius you take, that is called the radius of curvature, you take the reciprocal of that, that is the, the curvature at that point. So Kp is just 1 by Rp. Okay, but the problem is that the orientation of the curve tells you, if you change the orientation of the curve, then one side will become concave, the other side will become, it will change from concave to convex, and you have to keep track of this. Okay, so the moral of the story is that when you look at curvature, you have to take a signed curvature. Okay, and then you can do the following thing. What you do is, for this thing, see what is the philosophy of the Gauss-Bonnet theorem? Total curvature is some angle. The total curvature is always an angle. That is Gauss-Bonnet theorem. If you want to say it in the barest minimum words, what is Gauss-Bonnet theorem? It tells you the total curvature is an angle. So basically, you see what is happening in the case of in the case of the sphere. What are we getting? In the case of the sphere, what I am getting is that the total curvature is actually 4 pi. That's an angle. Okay, and more generally, if you take a G torus, the total curvature is actually 4 pi times 1 minus G. That's also a multiple of 4 pi. Anyway, that's an angle. Okay, so you always get this thing that total curvature is actually an angle. All right, that is how the Gauss-Bonnet theorem looks. But why is it that this is happening? Why is the total curvature an angle? Why are you getting an angle? Okay, so you have to understand that first. Okay, no, the sine curvature is that you have to put as extra sign if the normal. So the idea is like this: for the sine curvature, what you do? Suppose the curve is. So let us take this curve. Suppose you are moving like this. Okay, then what happens is at the particular point where you are calculating the curvature, what you do is that you draw so there is a tangent, and then the idea is you define, so this is the tangent, then you rotate it exactly by 90 degrees. Okay, you add plus pi by 2 and you get what is called a signed normal. And the point is, you have to check whether the center of curvature from that point is pointing towards the signed normal or away from the signed normal. If it is pointing away from the signed normal, then the curvature is negative. So in this case, the signed curvature at this point is actually minus 1 by Rp. That's because the signed normal is in the other direction. Whereas, if I had taken the orientation in the other direction, okay, instead of going like this, if I go like this, then the sign curvature will become positive. So you have to keep track of that vector. That's what the sign curvature, it tells you on which side of the curve, as you are moving on the curve, the sign curvature will become negative if the center of curvature is on the wrong side of the curve. And the wrong side of the curve means it's the right side of the curve is the side of the curve that is given by the orientation. So here, if you look at it, this curve, the area that it will cover will be this left side, because that is what lies to the left of the orientation. But the circle of curvature is on the other side. So you are getting a minus sign. You have to keep track of that. Okay. Now, if you don't give the sign, then it is not a well-defined function. And unless you have a well-defined continuous function, you cannot integrate it. Okay, so you do this. Now here comes a very interesting thing. So as I told you, Gauss-Bonnet is the total curvature is always an angle. Why is this happening for a curve? See, this is happening for a curve because of the following very beautiful thing. The sign curvature of a curve is actually the rate of change with respect to arc length of what is called as a turning angle. Basically, it is the rate, see, the curvature is actually the rate of change of the tangent direction, if you want. Okay, or it is the rate of change of the normal direction. So if you keep that as a reference, the curvature is actually rate of change of the normal direction, which is the same as the rate of change of the tangent direction. You have to make an adjustment to make the arc length to be the parameter, okay, so that it is unit speed. That's a technicality. But the point is, curvature is just acceleration. And acceleration is what? Change of velocity. Velocity is what? Tangent direction. Velocity is given by the tangent direction. Okay. So it's rate of change of the unit tangent or unit normal, whatever you want to take it. So but how do you measure rate of change of a unit vector? It's only by the angle that the unit vector rotates. Therefore, curvature is actually rate of change of a certain angle. So if you integrate it, what will you get? You'll only get an angle. That's why when you integrate a curvature, you get an angle. So what is going to happen is that, if I calculate integral over gamma 1 ksp ds, if I do this, what do you think I'll get? I'll get integral over gamma 1. ksp is what? Is d phi s by ds. Okay. And by fundamental theorem of calculus, what you will do, you will do it informally, but it's not correct. You will cancel this ds, and then you will say integral and d will cancel. All that you will say, and then you will say it's phi gamma 1 final minus phi of gamma 1 initial. This is how you do calculus, right? How do you integrate? How do you integrate 0 to pi by 2 sin x dx? What you will do is that you will write integral 0 to pi by 2 sin x is d of minus cos x by dx of minus cos x dx. Then you cancel out this dx. It's not correct, but still it's all right. And then you will take this minus cos x, this integral, and this d will cancel. Okay. And then what you will do is that you will just put upper limit minus lower limit. No, this is what you do. This is what is called one of the fundamental theorems of calculus. It's called the Newton-Leibniz formula. That's how you do integration. So basically that's what I am doing. So if you integrate curvature, what will happen is, curvature is rate of change of angle. So you'll get final angle minus initial angle. That's all. Okay. So basically what is going to happen is that is the reason when you go around and calculate, always you get when you integrate curvature, you always get an angle, at least for a curve. All right. Now you imagine what is going to happen here. If I integrate over gamma 1 and then add it with integral over gamma 2 and then add it integral over gamma 3, that will give me the total curvature, right? That is the total curvature. If I add it, what do you think I'm going to get? Okay. Can anyone guess what do you think you will get? What is integral? What is the total curvature? This will be integral over gamma 1 plus integral over gamma 2 plus integral over gamma 3 of ks of p ds. So let me do the following thing. No, you are not supposed to get a function. This is a definite integral, right? You are supposed to get a number. and that's going to be an angle. So what are you going to get is my question. So the point is that this is going to include all these angles. This is going to include these angles. See, because our original question was, if I take a twisted triangle like this, what is the sum of those angles? How are they related? So differential geometry actually says the sum of those angles is actually connected to the sum, total curvature. So what do you think you're going to get? So actually, so let me tell you how it's going to be. See, you take this guy, okay? Then what you do is that you smoothen it out. Okay. Oops. Just hold on. Let me smoothen it out like this, and like this. Okay. If you smoothen it out like this, then my new curve will be like this. Okay. Now, if you take a curve like this, which is a smooth closed curve, simple curve, what will be the total curvature? What is the integral? Suppose I call this as capital gamma, integral of gamma k p ks p d s. What is it going to be? You can even, for example, just think of a circle. No, it's very, very simple. See, what did I tell you? When you integrate along a curve, sine curvature, you get final minus initial. Final angle minus initial angle. So I start with the circle here. Okay. Then I go like this. Angle has gone to 90 degrees. It's gone to 180. It has gone to 270. And I come back, what will it be? 2 pi. Answer is 2 pi. Obvious. And this will not work only for a circle. It will work for any simple closed smooth curve. Simple curve means it should not cross itself. Because see, it's very simple intuition. You go around once, your tangent has to turn only by 360 degrees. That's all. So this is a very deep theorem. Okay, it's deep because you have to write. See, everything here is easy to understand. The deep thing is because you have to write a proof for it using calculus properly. So this is what is called as Hopf's Umlaufsatz. Okay, Umlauf in German means rotation. Satz means theorem. Umlaufsatz means Hopf's rotation theorem. It says a very simple thing that if you take a simple closed smooth curve, okay, smooth means at every point there is a tangent that is continuously changing, and it's closed means it's like a loop, and simple means it doesn't cross itself, so it should not be like an 8 or something like that, figure 8 or something like that. Okay, for such a curve, if you are going in the correct orientation, you will get 2 pi. If you go in the other orientation, you will get minus 2 pi. That's all. Because I told you it's sine curvature, so sine of the angle matters. If I go the other way around, I'll get clockwise 2 pi, and that is to be taken as minus 2 pi. Anti-clockwise 2 pi is taken as plus 2 pi. Okay. Then it's okay. See, it should not intersect. It doesn't matter. It can come very close, but it should not cross. And it should be smooth also. Yeah, if it is, you're asking if it is intersecting, what's going to happen? There's a theory for that. You have to use more math. It's not that it's doable. It is doable. So that's intersection kind of theory. There is something for that. Okay, but this is the simplest case. No, why I said this is because this is an important theorem, but this will tell you something. See, so you see, now give me the answer to this. Okay, see this portion, this red portion is your gamma. Okay, whereas this violet thing that I have written down is gamma 1, gamma 2 and gamma 3 like this. Okay. Now, what do you think will be integral over gamma 1 plus integral over gamma 2 plus integral over gamma 3 total curvature? What do you think this will be? See, had it been this red thing, I would have got pi. Okay. But because of this, what is going to happen? See, look at this part of the picture. See, here what has happened is that, if I calculate integral over gamma 1, this integral over gamma 1 will give me, basically the angle here minus the angle here, right? Wait. No, you won't get 0. Wait. See, the integral over gamma 1 will give the angle for this vector final minus angle for this vector initial. Okay. Then, so I will call this as 1, 1 and 1, 0. Okay. Then integral over gamma 2 will give angle for this vector, which is 2, 1, minus angle for this vector, which is 2, 0. Right? And then integral over gamma 3 will be angle for this vector, which is 3, 1, minus angle for this vector, which is 3, 0. Right? And these differences in angles is what is going, these are the differences in angles. See, but what I want you to understand is when you take something like this, okay, at the edge it's almost like this. Okay, if you approximate to the tangent, because it's only the tangent direction. So basically what is happening is that you're going like this and you're coming like this. So you're going to get, what is the difference in the tangent angle? It's going to be this exterior angle. Do you see that? So you're getting pi minus that exterior angle. Do you see that? You're getting pi, see, what is happening is that if you had smoothly turned, there wouldn't have been any problem. What you're doing is at some point you're going and then abruptly turning like this. So it's the exterior angle that you're going to pick up, right? So what is the, so if you add all these things, please be careful. If you are supposed to add the exterior angles, okay, but the exterior angles are pi minus the interior angles. So what you should get is 3 pi minus alpha plus beta plus gamma. This is the angle. This is what you are supposed to get. Okay, but also use the Umlauf stats. See, use the Umlauf stats also. Then what will you get? So let me help you think. See, had it been smoothened out like this, you would have got 2 pi. But what you have done is, if you don't smoothen it, okay, there is this extra term that's going to be contributed at every edge because of this sharp edges. So what you will get is, you will get the original 2 pi minus this. This is the extra, you have to take this out. This is extra you are getting because of the jump in the angles. If there was no jump in the angles, this term would have vanished. Okay, this term would have vanished. Okay. Yeah, if it was an ordinary triangle, okay, then I will get 3 pi minus sum of the 3 angles will be pi. So I'll get 2 pi, and 2 pi minus 2 pi I'll get 0. So see, 2 pi is what you should have got, but you are getting this x. You have to subtract this excess that's coming out of the curvature. So, and what is this? This is just alpha plus beta plus gamma minus of pi. So what is the significance of this alpha plus beta plus gamma minus pi? You see, had it been a spherical triangle, the difference is actually the area of the triangle, and the area of the triangle there is a total curvature. In the plane curve case, what is happening? The difference in this angle is also the total curvature, but now this is the curvature. This is the sine curvature of the bordering curves. So you see, this is also a Gauss-Bonnet theorem. Okay, and this is for a curved triangle. By the way, this is a curved triangle on the plane. Okay, so I should say this is on the plane. Now, just to complete my talk, I will just say give one more situation. What if you took a curved triangle, not on the plane but on the surface? Okay, so that is a last step. So what you do is you do the following thing. You have some surface, some curved surface. On the curved surface, you take some curved triangle lines. Okay, Again, you have gamma 1, gamma 2, gamma 3. You have all these alpha, let me say alpha, beta, gamma. Okay, and you have this region here. Now what is going to happen? Now mind you, not only the edges of the triangle are curved and lying on a surface, they are not necessarily geodesics. Plus, the triangle itself is not flat, it is kind of curved. What do you guess is going to happen? Again, you are going to get the same thing. You see, mind you, so this is total curvature. So total curvature is this, is what you are getting. So again, you will get total curvature will be alpha plus beta plus gamma minus pi. You will get this, okay? And here, what is the meaning of total curvature? There are two things happening now. There are two types of curvatures. In the edges, you have the integral over gamma 1 plus integral over gamma 2 plus integral over gamma 3 of the what is called as a sine. So I will call it as Ks, and this should be the sine curvature total, okay? And there is also a curved portion in the surface in between, okay? Interior surface. And in the surface, what are you supposed to do? You are supposed to take Gaussian curvature. So you have to take integral over the interior of the triangle of K P D A. So what I want you to understand is now the total curvature has two terms. There is a curvature due to the two-dimensional surface that you have to add, and that curvature is a Gaussian curvature, you have to add it. Then at the edges also you have to add the curvature. And these edge curvatures have to be taken carefully. They are what are called as geodesic curvatures. Why it's called geodesic curvature is because you see, if you put a curve on a surface, the curvature can be in any direction in space. There are two components. There is one component which is normal to the surface. There is one along the surface. It's the one along the surface that's called geodesic. Geodesic means on the surface. Originally, it was supposed to mean on the surface of the earth. That's why the word geo. Okay. So the point is, here again, if you calculate the total curvature, you will get alpha plus beta plus gamma minus pi. Okay. And this is the Gauss-Bonnet theorem. Now, do the same business. Take any surface of genus G, net it by triangles, and use this formula. Okay, then you will get that the total curvature will be 2 pi times the Euler characteristic, and the Euler characteristic is given by V minus E plus F, and that will be 2 minus 2G for a surface of genus G. Okay. So that is Gauss-Bonnet. No, you are asking why this is happening. You are asking for a proof of that. Okay, yeah, okay. See, so I no, that has to be proved. So basically, what I am trying to say is that if you are, if suppose the edge curves are geodesics, okay, geodesics. The point about geodesics is that they will the curvatures will be, you know, when you add it, a curve. So I am not trying to get into the proof of this, but I am just okay. Since you asked it, I have to tell you something about geodesics, but it's just that we got a little delayed because of we got a little delayed because of Professor Balakrishnan also started a little late. So I should since to answer your question, see what you do is, you do the following thing. So let me tell you, this has to be proved, but I want you to remember two cases. If the surface is flat, that means you are drawing this twisted triangle on a plane, then this term is gone, and you get sum of the curvatures of the 3 bounding curves, that is equal to alpha plus beta plus gamma minus pi, right? That you have seen, okay? That I have more or less proved to you, okay? If suppose there is no boundary at all, and it is a surface, and you look at a whole surface, closed surface, then it doesn't have boundary, so there are no boundary curves, so this first term will vanish. Then a surface without a boundary, then the first term will vanish, then the total curvature will be only this. That in the case of a sphere, I have already told you that you are going to get 4 pi, because the curvature is constant, it's +1. So you'll get total area of the sphere, which is 4 pi. If you do it for other things, you will get correspondingly whatever. Okay, you will get 4 pi into 1 minus g you will get. Okay, so that is the other case. But this case is for a curved triangle whose bounding curves are not geodesics, and the curved triangle is lying on a curved surface. That is the most general case. Now, proof for that involves some mathematical calculations. You have to use calculus to prove it. So, for example, if you look at Presley, the proof is more or less there. It's not difficult, except that you have to do some calculation. But the idea is that I've already told you that when you are at least when you are adding curvatures of curves, why you get an angle? That's because the curvature is actually rate of change of an angle. So if you integrate it, you will get back the angle. Okay. Now you should ask me, similarly, if I take a surface without boundary, like a sphere or a G-torus, why is again total curvature an angle? Why am I getting 4 pi into 1 minus g? What should that mean? Just like for a curve, the curvature is rate of change of an angle. For a surface also, the Gaussian curvature should be change of an angle. And guess what? It is change of an angle. What kind of angle? It is change of what is called a solid angle. So you take a surface, at every point there is a normal. Okay. Now what you do, as the point changes, this normal you put it on a sphere. So this normal, so it's like, as you move along the surface, this normal will change, and then the corresponding normal on the sphere, unit sphere will change. Now that normal, the tip of that normal is going to fill out an area on the unit sphere that defines a solid angle. Have you heard of solid angle, steradian, right? And again, the beautiful thing is the rate of change of instantaneous rate of change of solid angle with respect to area now, because you're on a surface, that is the Gaussian curvature. Just like on a curve, the sine curvature is instantaneous change of angle of the tangent or normal with respect to some specific direction with respect to arc length. If you do it for a surface, the rate of change of the solid angle, instantaneous rate of change of the solid angle measured by the normal with respect to unit area, that is the Gaussian curvature. So if you integrate it over that area, what will you get? You will get a solid angle, and that's why you are again getting an angle. Okay. So in any case, that's how you are getting the angles. Okay. But the point is that what this angle is you are going to get is controlled by the boundary curves. It's controlled by the Euler characteristic in the case of a closed surface, and it is this connection which is basically Gauss-Bonnet theorem. Okay. So, incidentally, I wanted since there was this thing that you asked me, I just say that because, so you see, suppose you have a surface like this. See, what you must understand is if I draw a curve on this surface, okay, now if you think about it, the curve has a tangent, okay, then there's something special that's going on. You have to watch it carefully. You see, this curve has a circle of curvature. The problem is that that circle of curvature will lie in a plane that's called the osculating plane. That plane need not be tangent to the surface. So what will happen is that there will be some plane like this. On this plane will be in space, and there will be a circle of curvature like this, and this will be actually the acceleration curvature vector. and there is no guarantee that this plane is going to be tangent to the surface at that point. So what happens is that you get, if you draw the normal to the surface at that P, at that point P, this is a tangent, this is the curvature at P, okay, then this curvature and the curvature need not be in the normal direction. So what happens is that the curvature can be resolved into two components, okay, that it is going to be dissolved into a normal component and then a tangential component, and this normal component is what is called as the normal curvature, and this other component is what is called the geodesic curvature, because that is the one that is going along the surface. So this is called KP geodesic, okay. And when is the curve a geodesic? When the geodesic curvature is 0. That's obvious, right? Because if you just think about a sphere, you think about the sphere, suppose there's a curve like this, okay. Suppose I take, suppose let's look at just the case of circles, which are not great circles and circles which are great circles. So if a circle is not a great circle, it's going to be like this, right? And for this circle, just think about it, it's very, very easy to understand. You see the what will be the curvature vector, because it's a circle, you see the curvature vector will be like this. Curvature vector will always point towards the center of the circle. But you see, does this have a, when does this have a 0 geodesic component? Only if and only if this circle is a great circle. Because you see, the normal to the circle will be like this. If this is the center of the circle, the normal will be like this. And this vector here, it will have two components, as you can see. There will be one, so you know, if I extend it like this, so I will get a component in this direction. So you can see it will be this plus this, and this will be the normal component, and this will be the geodesic component. Okay. When will the geodesic component be 0? If and only if the circle is the great circle. That's why great circles are geodesics. Therefore, geodesics are exactly the curves for which the whole curvature is in the normal direction. There is no tangential component, no geodesic component. Okay. You understand? And what Gauss-Bonnet theorem says is that when you are doing this kind of situation, then you know, for the edges you have to take only the geodesic curvature, and for the interior you have to take the what is called Gaussian curvature, and that is it's the product of the maximum and minimum curvatures on the surface, which will occur at 90 degrees always. That involves some more math. Okay. Okay. So you should remember Gauss-Bonnet like this, as you know, curvature is always rate of change of an angle. Integrating that gives you an angle. How do you get that angle? That has got to do with the topology of the surface. If it's a closed surface with a boundary, it will depend on the genus. If it is a triangle, then you will get sum of the angles minus pi. Okay. Yeah. So I think it's already quite late. I've also taken you much of your time. So if anybody has any questions, please ask me. Otherwise, you know, of course, there are several little things you may have to write down and look at. Okay. But this is supposed to be a very classical theorem from about 300 years ago, and it has lots of applications, and it has lots of generalizations also. Okay. And for further details, if you are interested, you can look at Presley's book. Basically, with basic knowledge of just integration, differentiation, you can understand all this. Some vector calculus you should be able to do. But that's not a very big deal. Okay, it's doable. If you're willing to sit down for a few weeks, you can understand it. Okay. Yeah. Does anybody have any questions? If not, I think really the bondas and vadas are attracting you, probably because you must be very hungry now. It's like 1:30.
I had an idea for how we could prove that you always need a given number of parameters to try a scale. And the thing is, let's say you start out with a triangle. you project it onto a three-dimensional space. That will create a tetrahedron, right? And that projection involves taking each of the vertex and moving it and drawing a line into the third dimension. So you always have, and same for square, you project it, you will always have 2 times 3 in the case of a tetrahedron, 2 times 4 in the case of a square, so on and so forth. It's always going to be 2 times some integer, which is your 2-dimensional figure. Now, as this approaches infinity, you end up with a cone, and once you have a cone, you can deform that into a sphere because it has no holes, while keeping the number of variables constant. So it's always going to be an even number of variables.
Yeah, you can say something like that, but there's only one problem. This cone being deformed to a sphere is somewhat of a problem, because cone is, if you say cone is deformable, when you say cone, do you say, are you taking the full cone, or are you taking only one side? You have to worry about that. If you take only one side, then one side of the cone, you can flatten it to the plane. So one side of the cone is always deformable to the plane, but the plane is not deformable to the sphere. It's deformable to the sphere minus a point. So there is a problem with one point, which is usually called the point at infinity, which occurs in the stereographic projection. So the only problem with using one tip of the cone is that you are not really getting the sphere. There's one point you're missing out.
So let's say we stack 2 cones on top of each other. That will be 2 times some number, right?
Yeah.
And
Yeah.
we can ignore that one.
I mean, from the formula you are saying.
Three sides, quadrangle, and 2 are common. That's to NDA, that's for NDA.
That for any event. That's what you want to say. That's okay. That's fine. But I'm saying that, yeah, that's okay. That's right. That's right. That's right. Of course, that's right. That's right. So the point is, when you write a proof, the problem is always that, you have to reason and say that if you're saying some strange thing, then you have to give, you're computing an integer, you're getting 3n by 2, then you have to really worry, why am I getting, why n has to be divisible by 2, otherwise this will not be an integer. Okay, so you have to give some reasoning for that. Otherwise, immediately red lights start, there are flags that go off, and this is something wrong with the proof you always worry about. Okay, that's a way of rechecking whether whatever you're doing is correct. Okay, so I think I have taken enough of your time, and I hope that this only, so now if you draw, a curved, a funny triangle on a curved surface, and of course, by the way, if you do it for a triangle, then you can do it for a polygon also, because a polygon can be broken down into triangles. So if you draw a funny, curved triangle on a curved surface, what is the sum? How do you calculate alpha plus beta plus gamma? You know what it is. It is actually pi plus the total curvature. Okay, so that's what you have to understand. Okay, so I think I will stop.